How's it going, everyone? Welcome, Eulio Gonzalez here, and today let's gonna explore about is the functions, argument adapters, the point free, and then we can now jump into what we really care, which is closures. So this has been a very interesting video, a set of videos in a book from Kyle Simpson. Shout out to Kyle Simpson, a software engineer that has previously worked at several companies, and based on his experience, because he wants to integrate now this functional approach, this way of describing is or writing code. So the code is based on this mathematical proof, pretty much like when you go out to your restaurant, you don't need and pay bills. You don't need to know is the mathematical proof that 2 + 2 is equal 4, right? So you don't go through the arithmetics, the addition, subtractions, multiplication, and division, and to understand what is a number and why a number is called the way it is. No, you just simply use that to get an outcome. And this is exactly the things that we're going to explore here with the functional programming. Now, this is something very interesting, because at the end of the day, you want to now solve your own problems. In other words, so by the time that you look at a old code base or a legacy code base, or even if you have to write code to provide some certain fix bugs or feature, at the end of the day, you want to at least have a way to make that, to have that code, to have a high level of confidence that it will work as expected. So the code is provable. So the code can give you now a function call the outcome expected. This is the value proposition of functional programming, and especially when you're going into this journey, which is something that Kyle Simpson mentioned, is that at the beginning you might find yourself pretty interesting. You know, it's like, hey, this is a good stuff. This actually slightly improved my readability, so forth and so on. But as the graph suggests here, where the g-axis is now the readability and x-axis is the imperative and declarative, this shift amounts that is that as you push forward into the function, the FP, you now realize that this is not that easy as you might expect, right? This is also a very common phenomenon in learning something, the pit of despair, which is I really love the name of this, because now this is where the readability tanks, and this is the moment that you need to keep push forward as a way to, at the end of the day, or in the couple days, weeks, and months, you're starting to connect all of the dots and say, oh, now I'm starting to get it here. Now, because, as I mentioned before, the whole point of this is that wouldn't it be nice to have a code base that 80% of the stuff that we wrote or somebody else did, or we are going to, now behave the way that it is, okay? So we have a high level of confidence of that, so we don't need to actually test that. So we can focus this on things that we don't have that high level of confidence. And that is the side effects, or the things that go and that happens outside of the control of that function. And that's exactly what we need to talk about is in this particular video, the recap of how do we get here. So the goal of review here is that, hey, we're going to talk about functions and procedures. We also look at the adapters, okay, Here he mentioned that, but there is a middle point between that. We're gonna look at also at the shape of the function and the adapters, in a way of how can we create is now or write functions without being explicitly in the arguments that we're passing, known as point free. We also going to talk. Let me see if I put it here, because this is quite interesting. This course is not, or at least that diagram is not that accurate. Yep. And then we're gonna talk about its closures, compositions, immutability, recursion, list data structures, array, and FP libraries. So, but again, the whole focus on this is to recap about the functions. How do we get here? So we can now finally jump to closure. So, in functions, we look at the difference between functions and procedures, and at the end of the day, function is the relationship between the inputs and the computed outputs. So why this is important? Because there are certain rules that we need to apply to our functions as a way to get the benefits of FP. Otherwise, we're going to water down the benefit of FP, so we'll actually rip off the benefit of. Now, procedures are set of instructions that modify the state at some point of the application outside of that scope. Whereas in functions, to make our functions to get the benefit that the code is provable, that it's going to work as expected, we need to look at the concept of function purity. In other words, is that, as I mentioned before, one single input, one single output. So it doesn't affect the state outside of the scope of this. And because of that, it doesn't cause side effects. So these side effects are stuff that eventually we need to do. Let's say you need to write to a database or to do a network call to calculate some random numbers, or to change the state outside of your applications or outside of that function. For example, mutating some data structure, updating some data structures. Timestamp, you need to manipulate the DOM in the case of web developers, or anything that eventually, you can boil down this into anything that generates CPU hit or CPU time delays are side effects. So the thing is that because this function purity, at the end of the day, the whole point of doing this is to avoid side effects at function calls. That's where the value proposition of the pure function kicks in. So to know what a pure function is, we need to look at from the single snippet to a more broad aspect or more broad sense. So pure function here is quite interesting. It's quite simple, like this. There's nothing wrong with that. But this, you might say, hey, yeah, this is an impure function. Why? Because at some point we are now using something that is outside of the scope. In this case, C. But what happens if C, okay, in this file only execute this particular code? You know, you say this is the function, and this function or this file, it will run only this particular code. So what will happen in that case? Well, if we fix or if we set the C as a cons, all right, whether it's using the cons keyword to avoid redeclaration and redefinition, reassignment and redefinition of the variable and its argument, or even if you're using var, but that value is fixed, therefore this function is pure. The idea of this is that with function purity, or with the following techniques of returning a function with another function with another function, we are now is reducing the surface area in which those parameters or those arguments those parameters can be redefined, okay, or can be reassigned, therefore giving us confidence that this function will work as expected. So why this is important? Because as we're going to define our function purity, which is the same input, same output, the value proposition of this is that we have a high level of confidence that this function at function call behave the way it is, okay? And if that function for some reasons needs to have some sort of side effects, so how can we now is extracting the impurity from that? So how can we make is now those impure functions or procedures work with our pure functions? And that is, well, let's go to now here is look at least two techniques. One of them is the containing the lexical scope. All right, and I think this is quite interesting. Let me actually show you this. Okay, one of them is containing the lexical scope at functions definition, if you can do that. All right, again, let me show you this because this is critical for what's coming next. And let's get into this. Let me see, view file. Okay, in this moment, so we have now this global variable with this data structure as an array where you have the students, yada yada. But the thing here is that this is one technique, and we say technique because these functions declarations is now sorting that data structure, is affecting that data structure there, right? So one technique is to say, hey, let's go to wrap this function where the impurity happens into a function, into a pure function that is going to take the lexical scope, or going to contain the lexical scope and return a new copy of that. This is something that if you can have control of the function definition, in other words, here we are effectively creating is a closure, all right? Because by the time that we call this function here, right, it's a hey, because this function lives inside of this function, and we take a copy of the students here, of that data structure. By the time that we call this inside of this function, the students is now not the global reference, is this local reference. This is good stuff, because the other example is the brute force technique, which is, let me take a snapshot of everything and then restore afterward. What does it mean is that since you cannot have here is a function's declarations, it means that this is now a dynamic scope. So what you can do, in other words, is by the time that you call this function source student by ID, okay, it will now call is the student at the global scope. So once you do this, you are now effectively altering is that global reference. So this is something that we don't want. So how can we prevent that side effect? So we take a snapshot of everything here, okay, and then we restore afterwards. In other words, we're gonna say, hey, that students, so we're gonna have a copy of the original data structure, in this case the student, and therefore we're going to now say, hey, let's go to get this new data here and match with the student. Therefore we are mutating the global scope, all right, by the time that this function call is being called, dynamically, it will now use that student reference. It will now create a new one for that, and therefore, because now we modify is the global student reference, we need to restore afterward. That's what we say, hey, student is now the original student here. And then we return is a copy from that. So even though that we mutate that state by taking a snapshot of everything that it needs, and therefore you're going to now is restore afterward and return a new copy. This is a technique that, for example, for this brute force approach might not be seem feasible from, for example, taking a snapshot of your entire database or the entire dump tree. In fact, this is quite expensive. But again, for small stuff, for small data sets, you might have or you might want to use this. So these two techniques are actually quite powerful, because here we explore now concepts like function purity, side effects, closures like this, okay, lexical scope, and dynamic scope. So we have now a mental model of what's going on anytime that you talk about those concepts, lexical scope, dynamic scope. And these two concepts are crucial to understand now JavaScript. So you can now provide your services to fix and improve or debug or add new features to your clients. So that's good. That's also a way to have now high level of confidence in your code. And this is why we look at another important concept of functions as it is, which is the argument, the shape of the function. So functional programmers are obsessed with the shape of the function, pretty much like Lego blocks. So when you have now one Lego block, then you want to try to fit this with another one, all right? You want to build now a heavy falcon, right, or another spacecraft. So the idea is that functional programmers, they're quite obsessed on doing that, and it's because pretty much like Lego blocks, they want to see how they can fit one function with another. So that's why that's why we need to talk about, or that's why parameters and arguments, despite that they are being used interchangeably, they are technically different, and we need to know the difference. Now, what's happening? Okay. So the parameters in the pure functional sense on JavaScript context is the name of the inputs from the function definition point of view, and the arguments is the values that we pass when we call that function. So why this is important? Because we can define here as binary functions, which is the favorite shape of the functions a functional programming love, and the shape of the function is and it is more plain terms, the numbers of stuff and the shape of that you pass into a functions, and the number and the shapes of stuff that come out of it. All right, this is known as the type signature. Now this concept here, especially but at some point that you want to now change the shape of your functions, all right? Hey, these functions now receive two arguments and it receives one parameter or two parameters, okay? If you want to actually match those different functions each other, so now we look at this common patterns that, for example, in functional programming libraries are using. And the idea of exploring these argument shapes and how can we even create our own shape adapters is to, despite that it's not recommended to go and create your own, and if you do, try to make a peer or update your change to a popular FP library, is because it is much better for the overall community to get familiar or to work with stuff that we are familiar with. For example, is hey, we have now unity function, we have now binary functions, we have now flip. All right, when you want to actually is flip is the two arguments, right? The first and the second, like this. Or at some point, that might not be what you expect most of the time, but perhaps you want to, which is the reverse. It's like, hey, I want you to reverse all the arguments that I'm receiving here, all right, in order. That's why, for example, when you explore now the function called methods called .call or .apply is actually coming from this functional programming, and things are starting to make a lot of sense. So this call and apply, all right, where the call is you're going to now call these functions with all of these arguments in a comma separated value way, all right, or the apply is that you're going to now receive this collections or array of arguments, and then you apply to each one of them. So this is quite interesting, because now we're starting to see if the root of even the functional or the function tool provided by us in JavaScript and how the thing started to work, and how now that is very intertwined with the functional programming, as the name suggests, quite there, and how then that mix with, for example, the object-oriented programming, and then the asynchronicity topic that we're gonna see that later, but it's quite interesting to recap about that. But in any case, so after that, all right, in the shapes adapters like this, another shape adapter we commonly use exactly is to call arguments individually or via an array. Again, this is now shapes adapters, argument shapes adaptations. So we are looking at things from that angle, all right, from the FP approach, so we can get ourselves familiar with what's next, and that is the point free. So with point free, right, since the idea here is that we're still talking about the shape of the function, and if that shape now is the same, all right, in terms of the arguments that it receives, so the functions, for example, functional programmers call the arguments data points. And this is interesting because if you remember your class from 8th grade, that when you have now, for example, fix one of the coordinate here to a certain value, and then you do something else, right? Perhaps not in this approach, but more in the 3D space, where you, for some reason, let me put it this way, like that, to make it simple, okay? So when you do this, you say, hey, let me now fix is, so you can see here in this function, it's like, hey, we can now think in terms of several dimensions here. So if you say, hey, let me fix now the value of one function at certain point, and there the other can vary. So we can now is, for example, if you fix in the g-axis the value of 1, all right, so it will give you now 2 in this example. It will give you 2, and then whatever other value in x, it will give you now is this line, right, with a different magnitude. But this is interesting. So because this same concept of something that we thought that we didn't even care, or that we didn't even thought that that was something useful, at least in our daily life, okay, is now useful for real. So this point free, as I mentioned before, is that they talk about the points as the arguments that this function receive, okay, or the input that this function receive. So if a function that we're passing has the same shape, couldn't we interchange the shape of this function or the shape of these adapters? So this transformation into something like this, a get person, and then you pass out the render person, is known as equational reasoning. Not equality in terms of its values, is equally in terms of its argument shape, right? So this is when now you have to be careful, because once you look at this, you say, oh, this is quite good, this is powerful, this is awesome, I would like to look and use in every place. You have to be careful about when you're going to use this, or at least understand what is the value proposition that you want to get from this, because this point free is going to tax your code readability vastly, because now as the complexity grows, this actually make it hard to read if you're not quite familiar, one, and second, if you are not somebody that see the value proposition of this point free. And that's why we focus is on looking at that shape, at the point free. So let's go to talk about that.
So what we want to the physical letters in those words.
Mm-hmm.
So what we want to do is we want to get to that idea of the shapes being equal with each other. Here I have an is-odd function. Pretty straightforward. It uses the modulo operator. So any value modulo 2, if it returns us 1, that means it was an odd number. If it returns a 0, it's even. Okay? Very basic math concept there. But if I wanted to find the is-even function, there's a couple of ways that I could have done it. I could have said is even, and on line 6 I could have said v mod 2 equals 0. And that would work just fine. It's mathematically accurate to say that is even is v mod 2 equals 0. But I did it a little differently. I defined is even in terms of the is odd function. And specifically I negated it. Because we have a binary here, something that's either even or odd. It's not both and it's not neither. It's either a number is either even or it's odd. So I'm asking the question here, if I take this is even function and I define it in terms of is odd, as opposed to doing this v mod 2 equals 0, what have I purchased with that choice? What benefit am I getting from defining?
Mm-hmm. So from the following example, I could define is even just using is the mod operator, okay, which is good, but the thing here is I define it in terms of is odd, is in terms of the negation of is odd. Why are we doing this? Why are we doing this? What am I purchasing? What am I buying? You know, what am I buying here? You know, what am I buying? And what am I buying here is that now the relationship is that now when I use the when I call the functions in my program, the relationship here is more explicit. Okay, the relationship here is more explicit, which is something that any programmers are agree that it's better to be descriptive or explicit than implicit. However, since we are now relying on mathematical proof, okay, that this thing work, that these things work as expected, when we call this function, okay, which is something that all programmers agree is better to be descriptive or explicit rather than implicit. However, since we are now relying on mathematical proof that the things work as expected when we call this function, in this example of using point 3, okay, I'm just going to put it here. So in this example below of using, in this example of using point 3 below, which is what we're going to show you later on, we are saying that in some scenarios, being implicit is preferable to look or to understand the relationship, okay. So in this example of using point 3 below, we're saying that in some scenario being implicit is preferable to understand the relationship between functions. That makes a lot of sense. That makes a lot of sense. Let's keep going.
Finding is even in terms of result. And the answer I would say is I have created a more visible relationship between the two functions. I have said that is even is the negation of is odd. Whereas if I just done b mod 2 equals 0, that relationship would exist but it would be completely non-obvious. Here I am attempting to make it more obvious, the relationship between is odd and is.
So by making, so by writing the, so by writing the relationship, so by writing the relationship between the mathematical, okay, so by writing the relationship between so by writing the relationship between the mathematical computation, which is v mod 2 is equal to 1, okay, is to say, hey, is this number is even, if this number is odd, sorry. If it is, good, return that, right? So by writing the relationship between the mathematical computation, okay, or by defining the relationship between the mathematical computation and the semantics, that is odd, okay, and the semantics that is odd, all right. So by defining the relationship between the mathematical computation and the semantics, we can clearly express to the user or to the reader the relationship between we can clearly express to the reader the relationship between functions. Okay.
By defining one in terms of the other. So it's not just about saving keystrokes. A lot of times you hear people say, well, blah, 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 dry. Don't repeat yourself, right?
Exactly.
That might be why a lot of people...
It is not saving keystrokes.
I'm not saying that there isn't benefit there. Okay.
Or don't repeat yourself.
And sometimes hamper the readability of the program. But actually it turns out,
But
sometimes in
is
functional programming, it is better
to improve.
So we don't want to take dry as like a religious, artifact, like, oh, I have
But it's to improve the
everything is using the,
readability. But it's to improve the
Here, we're not doing
readability relationship between models, between functions.
And by thinking that way, we actually got ourselves 90% of the way being able to answer this question, which is, could I define the is-even function in a point-free way? Could I define it in terms of is-odd without having to list out that b that's being passed in? Because there's the point. This is a pointed.
Similar to the bill.
Before I even show you how to do the point-free, we probably should have motivated what is the point of the point-free? Like, what are we buying? Well, what we're doing is we're moving to that declarative style. When we have points, what we have is an imperative style that routes data from the input. But when we use point-free style, we have a declarative thing. Here's a strange phenomenon that I've seen with the idea between imperative and declarative. Because
similar to the utility bills.
To me, imply that imperative would be implicit, since the words
to a restaurant.
That it's reversed. It turns out that imperative
To
mode
a
is generally more explicit.
when you go out,
And declarative mode is
when you go out
implicit.
for
Now, when
a
you stop in 100
sushi
somewhere, and you ask them the question,
with
is it
somebody,
better explicit or implicit, 99 out of 100 are going to tell you
and you get the bill
actually suggesting there is that in some senses,
to see if
it's better to be declarative
that
and allow the
sushi
that are in our application, either in the language or in our
was worth
unnecessary details.
the
Because it's not
price.
important for the reader of this code to see B on line 5 being passed on line 6. That is an unnecessary detail. If I can define this in a point 3 right,
So we can see the relationship much more
glance at and realize,
clearly
is even as the
because it affects us directly.
If you can agree with me that it is beneficial from a readability perspective, how are we going to accomplish it? We're going to accomplish it by creating a utility that adapts the shape of a function. Exactly like we did before with Hoffs, we're going to make another Hoff. Actually, we don't need to invent one. One already exists. I'm just going to tell you about it. Let's think about a Hoff, a higher order function called not. And this is, by the way, often referred to as complement in functional programming libraries. I don't like that name. That's confusing. So I like to use not. Sometimes I use negate. Sometimes I use not. I almost never use not. But anyway, if you're looking it up, you'll find it's called complement for something random. But what it does, it takes the function fn line 1. It makes a new function that's negated, line 2, and all it does is call the original underlying function with all the inputs and return the output. But it does line 3, that little exclamation mark indicates it. So now, when I declare
here we create a Hoff utility,
and what I would argue is not only is line 11
by the time we call it,
it is even more clear
we
the
negate it.
Is odd and is even now, right? You can very clearly see that is odd is a negation, that is even is a negation of odd. That's where we get the readability gains in functional programming, specifically in point design. Define one function in terms of another, you know, the relationship between them much more clear. You allow the how, the imperative details, to be implicitly hidden through a declarative style. That's the big takeaway from all the functional programming. You can almost stop right here and just get that. And you've gotten a huge nugget of wisdom out of functional programming. That's the takeaway. You allow the how, point three side. You define one function in terms of another, and you make the relationship between them much more clear.
You define one function in terms of another, and you define the relationship more clear. And you define the relationship.
Specifically in point three side. Define one function in terms of another, and make a relationship between them much more clear.
You define one function in terms of another. You make the relationship more clear with another. But again, here we're using is now this Hoff, these high order functions here, to say, hey, give me this high order function here, okay, and then I'm going to, whatever the value come out of this, I'm going to negate that.
You allow the how, the imperative details, to be implicitly hidden through a declarative style. That's the big takeaway from all the functional programming. You can almost stop right here and just get that, and you've gotten a huge nugget of wisdom out of functional programming. That's the big takeaway from all the functional programming. You can almost stop right here at the details to be implicitly hidden. One function in terms of another, you make the relationship between them much more clear. You allow the how, the imperative details, to be implicitly hidden.
So you allow the how, the imperative details to be hidden. Exactly. You allow the how, the imperative detail to be hidden, to be implicitly hidden. You allow the how, the imperative detail, to be implicitly hidden, to be implicitly hidden. So you allow the how is this argument, how this is passed through a declarative style of coding. Through a declarative style of coding.
That's the big takeaway from all the functional programming. You can almost stop right here and just get that. And you've got a huge nugget of wisdom out of functional programming. That's the key idea. All right, let's do an exercise to practice these point-free refactoring techniques. In this exercise, you've been given several different functions. The readme will indicate 3 of them: the output function, the printf function, and the isLongEnough function. Those 3 functions you need to modify or refactor them to be defined point-free. So if you look in the exercise file, you'll see they're all at the top. You have the output function, the printf function, and the isShortEnough function. The isLongEnough function. Those are the 3 functions that you want to refactor to be point-free using the techniques that we talked about. There are listed in here a number of hints, and these are important for you to actually complete the exercise. So make sure you check out the hints in the readme. They should help you with those 3 factors. Your test cases essentially are that the first one should print hello, then nothing should be printed by the next 2, and the last one should print hello.
Exactly, which is a hop function here should print it, which is the function that you're going to receive.
Your test
Isn't it short enough? Is short enough? Is long enough?
And these are important for you to actually complete the exercise. So make sure you check out the hints in the readme. They should help you with those 3 factors. Your test cases essentially are that the first one should print hello, then nothing should be printed by the next 2. They should help.
This is the printf function, like this. Should print this. It's going to receive now the function in it itself, the printf initially, and then it's going to call that with the actual message and say, hey, if should print if, then you're going to call the output here.
We're listed in here a number of hints, and these are important for you to actually complete the exercise. So make sure you check out the hints in the readme. They should help you with those 3 factors. Your test cases essentially are that the first one should print hello, then nothing should be printed by the next 2, and the last one should print hello.
So that'll be all for this video. Take care. Bye-bye.